MIT and Ascending Technologies. None of them want to come up and model our helicopter for you, but the rest of our team's in the back. We got Marcus Ashtelek, Michael Ashtelek, myself, Daniel Garden, Rachia He, Garrett Heeman, Sam Prentice, Jan Stumpf, and Anton De Winter, and very importantly, our advisor Nicholas Roy, who's in the bottom center, who unfortunately wasn't able to join us down here for the lovely weather in Puerto Rico, but played a big role in our development and entry here, so definitely deserves mention. So before we go into all the details, let's just show a video, because videos are fun. The judges got to see this video earlier, or yesterday, but the rest of you did not. So this video goes through basically our outline mission in the competition arena that we set up in our lab. So those renderings are real 3D renderings that we get off the vehicle in real time as we're flying around. We just saw the vehicle take off, detect the window, fly through it, and now it's going to begin flying around and exploring the environment, trying to identify free spaces and search until it finds the blue LED. So as you can see, the vehicles fly stably and provide a nice platform to do this higher level exploration and mapping. In this process, we see that the red lines, the trajectory that has fallen to go to the little pink points, which are the frontiers that have been detected that the vehicle is trying to go to. And so the vehicle flies around until it has uncovered pretty much all of the explored space, and/or until we successfully detect the LED. This is just more footage of it flying around. Pretty soon we should see a action shot where we turned up the speed a little bit. So right now it's flying pretty stably, but we can also fly up to about 1 meter a second. We're not going to actually do that for the competition because it's not quite as stable, but that was pretty exciting to see. And this is the final portion of the mission where we detect the LED, we sort of home in on it with our controller, and then we sit right in front of it, make sure we get a good image, and then we're done. And let's stop the video there. So the key technical challenges that we identified to complete this mission, first and foremost, we need to design and operate a micro-air vehicle that's capable of just flying and executing the mission. So that involves the mechanical design as well as the on-board high rate attitude estimation and control. So that, as many of you, the teams know, that was a critical portion of this entry. Once we have that, though, we need to figure out how to do accurate position estimation, and such that we can actually stabilize the vehicle at a designated position in the world in real time, for which we use laser-based scan matching to back out the position, and the laser also gives us the ability to map the environment and can make those positions consistent on a global scale. Now, once we have those maps, we can then do even higher level planning of sort of the autonomous exploration, where we search through the free space, and then, as you all know, the last part is just finding the gauge, which is the end goal of the mission. So to accomplish this mission, we sort of came up with like a wish list of sensors that we would like to have. So we had done some previous work with the Hokuya laser range scanners, but they only give a 2D view of the environment, which is quite useful. You can use the mirrors, so we use right-angle mirrors to deflect some of the beams that come out of the laser beam down to the ground to estimate our height very accurately. So you get this sort of 2.5D view, which works very well, but we wanted to be able to do more 3D planning. So we also mounted a pair of monochrome stereo cameras, which allows us to perform visual odometry, as well as obstacle avoidance in real time. And also, because we want to get a sort of clean overview of the environment around us and be able to detect the blue LED, we mounted a third color camera. So connecting all these and getting all that data to the base station proved to be rather challenging. We had previously used the Gumsticks computers that some of the other teams had been using, but we wanted to look and see what else was out there that would allow us to use the high-speed USB 2.0 connections that these USB cameras provide, as well as a sort of higher bandwidth 802.11n Wi-Fi connection. We found that this company Lippert Embedded out of Germany had this 1.6 gigahertz Intel Atom computer on module board, which is a little less than the size of a credit card. And it looked perfect for our needs, except for the fact that it just has a 220 pin connector coming out. So it had all the signals we needed, but we didn't really have an easy way of accessing them. And all the sort of breakout boards were sort of larger, very small form factor for like a full-blown computer, but still larger and heavier than what we wanted. So we designed our own lightweight periphery breakout board, which gave us a bunch of USB ports and serial ports and display connector for debugging, and all that weighed in at under 80 grams. And the really nice thing about this is that because it's a standard x86 computer, we can just run stock Ubuntu 8.04 just like we have on our ground station laptops. We don't have to deal with the cross-compiling, and we can use off-the-shelf USB Wi-Fi drivers or PCI Express wireless cards just like you have in a laptop. So basically we have a fully functional for what we need, no display, no battery obviously, but fully functional for what we need, sort of netbook style laptop on the quadrotor. Unfortunately, when we added all that up, we realized that the Sending Technologies Hummingbird quadrotors that we had been very comfortable and used and worked very well didn't quite have the payload to carry this. So we worked with them to develop a new vehicle, which is shown here, and the real version is there, that would have considerably more payload and allow us to carry all the sensing and computation that we wanted. One thing you may notice that the front rotor is actually upside down, and that was done to increase the field of view. So we didn't want this propeller spinning in front of the cameras, and so to get it out of the field of view, we put it on the underside, and one would think that might make things unstable, but because the quadrotors are already being actively controlled, and you have to do enough sort of attitude stabilization to handle moving payloads and stuff, the net effect of just flipping the rotor upside down was well within the sort of stability margin of the controller. So here's a sort of close-up of the electronics rack. We didn't, we wanted to be able to put these sensors and stuff on, but we didn't know that we would end up using all of them. We didn't know how we necessarily want to attach them, what the form factors were, so we made a sort of stackable electronics rack, which allowed us to sort of plug and play different pieces and sort of cleanly mount and detach the entire sort of sensor subsystem, which is by the way, is also sort of vibration damped. So the laser and cameras are actually sort of suspended between two rubber dampers to just isolate the vehicle noise from them. So final technical data on the vehicle itself. The total empty mass of just the vehicle without any of the sensors or battery is 540 grams. With everything on there, it's about 1460, plus or minus a little bit, depending on the number of zip ties and the amount of E-tape on there. We get, with the 4,000 milliamp hour 3-cell LiPo batteries that we use, we get a flight time of about 10 minutes. And these motors are actually incredibly powerful, and at full bore, they would give us, all four of them would give us a combined thrust of about 3.2 kilograms. In fact, one of our first tests was to put a full wine bottle on top of the vehicle and see if we could take off, and it just barely took off, but that was pretty cool to see. And the maximum dimension is about 70 centimeters. The vehicle is controlled by this same autopilot